So Monday we talked about the beginnings of probability, and we were looking at how to add probabilities together. Today we're going to look at some of the multiplication concepts, and we're also going to look at combinations and permutations. So if I wanted to know what's the probability that I'm going to choose a female wearing a red shirt in here, how would I find it? I'd count up all the females wearing a red shirt and divide it by how many people are in the room, right? Okay. If I was to say I'm picking a female and then finding one that has a red shirt, would the probability be the same? So you can start to see how wording will matter. Because now I've already chosen part of it. I've eliminated all the males in the room, and now I'm just looking at the females that are wearing the red shirt. So my probability changes. The bottom is no longer the whole class, it's just the females. So in that respect, we have what's known as a conditional probability. A conditional probability is an event that will occur that's based on another event that has already occurred. Okay. So this is where those wording really matters, and how you read things are really going to matter. I will say the wonderful complicated formula down the bottom is not nearly as complicated as it looks. The one big thing that's actually most important is this piece. That symbol. That means the probability of event A occurring given that B has already occurred. Okay, so it's A given B is basically how it's read. Yeah. Okay. So this over here, that's the intersection of A and B, and then that's the B. Okay. Let's finish writing it down, and then I'll switch over and we'll actually work on a problem. That doesn't require everybody standing up and trying to look around. Okay. All right. So here's data. So we got a market research study. They've looked at people ages 18 to 34, 34 to 35 to 50, and then over 50. And it was like, not like, or undecided. So what is the probability that an 18 to 34-year-old will like this product? How would I figure that out? Yes.
Would it be like 213 divided by the 513?
So there's one word missing in mine. I didn't say given. And that's the big difference. So if I was just looking at an 18 to 34-year-old that liked the product, I would do the 213 out of the 1403. Out of the full total. Okay, because I was just looking at this and that out of the whole thing. Okay, so that is just 213 over the 1403. If I had said, what is the probability given an 18 to 34-year-old likes the product? That word given now means I'd be looking at it over the 513. Okay, so that's really the piece that you want to see in there. So this question says, if an individual is between 35 and 50, so that's the same thing as they're giving you that piece of information. So saying that, what's the probability that he or she will like the product? So in this case, the 35 to 50 that likes it is 193, and we're doing it out of the 444. Because we're taking that initial condition. We're saying that they're between 35 and 50. What is it that they will now that given that, what is it they will like the product? Does that make sense?
Yes.
No idea what I just said, but yeah. Yes.
Where did the 300?
The total of the 35 to 50-year-olds.
I'll do that.
Yeah. The nice thing of this one is they totaled them for you. They don't always do that part. What's the probability that, what is the probability given that the product is not liked that the person was over 50? Yes. Correct. Okay. So I'm looking at this piece right here over the 600. Because I gave you the fact that they was not liked. Then what's the probability that they were over 50? It's 219 over 600. All right. What is the probability that a randomly chosen applicant has served in the military given that he is male? So what do we need? We need to know how many served in the military, right? 110. Out of how many? Right. We're only looking at the male, so it's out of 212. I'm confused on how the next one's worded. Oh, okay. Gotcha. So the next one says if 152 of the applicants have served in the military, what is the probability that a randomly chosen applicant is male given the applicant served in the military? So how many males served in the military? $110. It says 152 applicants served in the military, not males. I know that was the piece that messed me up. I'm like, wait a second, because I missed the of male applicants 110. So there's 110 males that served in the military, but there's more that served in the military. So there's 110 males that served in the military out of 152 total applicants that served in the military. Yeah, that's the English part that confused me too. I'm like, wait a second, I missed the of male applicants because I just assumed that was in the military. I'm like, they're changing that number. That doesn't make sense. So you can start to see how that. I told you the hardest part of this a lot of times is the wording, not necessarily the math. The math actually sometimes is quite easy. It's understanding the words. And this section, when we're looking at conditional probability, that wording becomes very important. Yes. Oh, that's what you're saying. All right, let's do another one of those. Hold on. Let's look at. All right. So computer software company receives hundreds of calls each day. Common installation mode, call them A, B, C, and D. Several of these problems result in the same symptom, a lockup after installation. So the computer crashes. Suppose that the probability of a caller reporting the symptom lockup is 70% or 0.7, and the probability of a caller having problem A and a lockup is 0.6. So if they're calling with the system lockup, they're at 0.7, right? That's the probability. So the probability of lockup is 0.7. The probability of a intersection lockup, because remember, intersection is the same as and, right? Is 0.6. Given that the caller reports a lockup, what's the probability that the cause is A? So they've said lockup, right? Yes. Huh?
Would that be 30%?
No.
Okay.
So remember that the probability is over, the given is on the bottom, right? And then what the intersection basically is on top. So since they've called about a lockup, the lockup's on the bottom. Because we've given that. That's the initial statement. We know that that's the case. And then what's the probability that A is caused given that? And that's the 0.6. That's the intersection. So in essence, it's 6/7. So, huh? It'd be 0.6 over 0.7, which if we multiply by 10, we get 6/7. Remember, you got to multiply the top and bottom? I just didn't divide it. I left it as a fraction. If you divide it, you get, I don't know. I can't do 7 top of my head. It's actually pretty high though. Hold on. 85% base or 0.85. So if they're calling me up and telling me their system's locked up, I'm going to assume it's A. And if it's not, then I'll go out of the other ones because there's an 85% chance of getting it right. What's the probability that the cause of the malfunction is not problem A?
4/7. Because that would be, because I'm assuming if the collector's one would be 1, so it would be 1. That would be 0.6 minus 1 minus 0.6 would be 0.4, and then 0.4 over 0.7 would be 4/7.
Okay. Do we know what the probability of A is?
0.6.
No.
Oh.
That's the intersection.
Oh.
Okay. So what's the probability that the malfunction is not problem A given the we know that this is the probability that it's A given a lockup, right? So this is the not Congress. I really can't think today. Complement. That's it. That's the complement of it. It's the exact opposite of it. So it's 1/7. Because I would do 1 minus 6/7, which is 1/7. So that's B.
Oh, now I understand.
Huh?
To say that, but I didn't want to sound stupid if I was wrong.
It's okay.
Okay. First of all, I will never make you sound stupid.
I just didn't want to get the no.
That makes sense. That makes sense.
And this is a lot of times I'll actually ask why more than anything. Right. So, but even if I say no, I'll ask you why that you said that. It was like, because again, when you think of something, we learn more from our mistakes than we do from success. So it's like when you get something wrong, being able to take that and explain out why that's the mistake and where to fix it is going to help you going forward, because you're going to get more stuff wrong on those homework assignments and tests than anything else. So like if you can understand like, okay, this is what I'm doing. Wait, no, that's not the right way to think about it. Then you'll fix your mistakes. So I'd rather that than you not actually answer it. Okay. It's more helpful. All right. Does that make sense? Yes.
For A, like, what equation is that following? Like, why would 0.6?
It's following this one.
Oh, okay.
It's the intersection of the two pieces. Basically, what happens when both those happen over which your initial condition was. And in this case, your initial condition was given, or was the lockup, so that's the 0.7. And the intersection of those was the 0.6. And since B is the exact opposite of that, or the complement of it, that's why it's 1 minus that, the 1/7. That's why I said, when I'm looking at this, I'm going to assume it's A, because it's 85% chance that it's A. There's a 50% chance it's something else that I'll work on later if that doesn't work. So my first line tech support is always going to assume A, and if it doesn't get that right, then we'll send it to somebody else. Which is why if you ever call it tech support, the first thing they ask you to do is restart your computer or restart your phone or restart whatever it is. Because 90% of the time, that will solve the issue. And if you turn around and tell me the computer's not on, I'm going to ask you to plug it in. All right. So when we're looking at the conditional probability, this piece right here is the most important part, right? That's the piece that's on top. Okay. That's the intersection. We talked about events that did not have an intersection, right? They were called mutually exclusive. Okay. So if we have two events that are, when we look at the conditional probability, and they always come out to be whatever the basic one was, then those two events are independent, which means they're mutually exclusive. They don't interact with each other. Okay. So the situations that we just looked at had that intersection piece. All right. But not everyone does. So sometimes they are mutually exclusive. And that's one way we can test to determine if two events are mutually exclusive is by doing the conditional probabilities. Okay. Odds are you're not going to do that very often. You're going to be able to look at it, tell that they're mutually exclusive, or be able to look at that piece. But that's what that means. Independent events or mutually exclusive events are very, very important when we're looking at multiplication. Because if they're interacting with each other, we need to take that into account when we're multiplying. So if we're going to look at multiplying probabilities, we can just take them and actually multiply all the different probabilities together to get my final answer. If they are independent, the intersection is literally just going to be the multiplication of those two pieces. And we can do this for any number of events. It makes much more sense when we actually do a problem and see it. All right. So you're playing a game. Coins flip, the die is rolled, and the card is drawn. So what's the probability? So first thing we have to ask is, does any of the three events impact the future events? No. If I flip a coin, it has no impact on the die. The die has no impact on the cards or the coin, right? So so these events are mutually exclusive or independent. They're separate from each other. So we can literally just multiply the three probabilities together to get my answer. So what is the probability of me getting a tail on the coin? Or 1/2? I'm going to tell you. So you can do this either way. You can use fractions or you can use decimals. My suggestion to you would be use fractions. I know everybody doesn't like fractions, but they're going to be easier for you to do because you're going to be able to find that number. And honestly, in some of situations, when you have to get the decimal, you're going to divide the fraction anyway, so it's one extra step. Like, what is the probability of giving me a 5 on a die? Right. You're not going to tell me it's 0.16666. You're going to tell me it's 1/6. So you already got the fraction. So don't make 1/2 50% and then do 1/6 for the next one. Make sense? Because then you're going to have to convert them afterwards. So it's easier to leave them all as fractions and then at the end just put them into and make a decimal at the end if you wanted it. So we're going to times it by 1/6. What's the chance of me getting a jack of clubs? 1 out of 52. So to find the probability of getting all three of those, I'm just going to multiply them. Now, remember how to multiply fractions? Multiply straight across. So the top is going to be 1. So it's 1 out of 624. Or if you need it as want it as a fraction or decimal. That's it as a decimal. That's all that rule said. See, it's much easier when I actually do out a problem and show it to you. Okay. Does that part make sense? All right. This is an actual case. This really, truly happened. I would have loved to have seen the judge's reaction when it happened. So on June 18th, 1964, at about 11:30, Miss Joanna Brooks was assaulted and robbed while walking through an alley in San Pedro, Los Angeles. Miss Brooks described the assailant as a young woman with a blonde ponytail. At about the same time John Bass was watering his lawn, witnessed the assault. He described the assailant as a Caucasian woman with dark blonde hair. As she ran from the alley, she jumped into a yellow automobile driven by a black man with a mustache and a beard. Several days later, the police arrested 2 individuals based on the descriptions provided by the assailant. The 2 suspects were eventually charged with the crime. During the trial, the prosecution called the professor of mathematics to testify. The prosecutor set forth the following probabilities of the characteristics of the assailant. So, the probability that it was a yellow automobile is 10%. They probably got that by looking at the DMV records and figured out that there's only 10% of all the cars that were registered were yellow. After I'm done with this, I'll tell you a funny story. Man with a mustache, 25%. Girl with a ponytail, 10%. Girl with blonde hair, 33%. Black man with a beard, 10%. And interracial couple in a car, 0.001%. Remember, this is 1964. That did not happen nearly as often as it does today. Are all these events independent? Well, so the question is, I guess, you'd either be a yellow automobile or not a yellow automobile, right? So the color of the automobile doesn't have any impact on the man with the mustache, right? Yes. Yeah. So basically, so The prosecutor argued that these are all independent values. Yes.
Well, I would say some of them are dependent values, but some of them are independent values. Like yellow automobile has nothing to do with the girl with the ponytail, but wouldn't it be that you're looking for black men that are in a known or in some kind of relationship with a white woman, and vice versa?
Well, that's what the interracial couple is.
Yes.
So they got that part. But if each of these probabilities aren't related to the next one, and this gets overturned afterwards, they get convicted of this, then it gets overturned for that exact reason. The other person goes, wait, there can be some interaction between these, and where'd you come up with your numbers? So if we assume they're independent, we can just multiply all these together to figure out the probability that I'd find the person, right? Or how many different people there would be. So if we multiply all those probabilities together, and what do you get? Somebody else do this on a calculator. You all have one. You probably got in your calculator something like this. You want to turn it sideways? Yeah. That's scientific notation. It means move the decimal 8 places. Okay, that's what that means on your calculator if you get it. It might have said 10 times, depending on the calculator you have, it might say 10 times, but all your phone calculators probably had the E. So it just means move the decimal 8 places. So that's how I got the 0.70825 there. So it's a really, really, really slim chance, right? That this would happen. So they figured they found the person. Obviously, they're the ones who are guilty.
That's the logic right there.
Exactly. So here's my funny story. So I lived in Hartford for growing up and everything else. I moved down to Norwich in 2006. And then I moved back up to Hartford in 2013. Or no, actually, yeah, it was probably 2006. And then I moved back up to Hartford about 7 years later. However, right after I moved here, so I lived on the west end of Norwich, but they're on down the Lisbon side of Norwich. So I drove down to Lisbon's Walmart. Now at the time, I had a yellow Monte Carlo with blackout tints on it. Okay. So I go to Walmart, we buy some stuff, and we're driving back to Norwich. All of a sudden, I see a cop behind me who put on his lights and pulled me over. Like, I didn't do anything. Cop comes up, tells me to get out of the car, goes over to the other side, asks my wife, has he been with you the entire time? Come to find out, somebody in the Walmart parking lot had claimed they were robbed. Their purse got snatched from them, and the person took off in a yellow car. Obviously, there's not tons of yellow cars. He ran my plates, and they still said they were from Hartford. So he pulled me over, assuming it was me. So these type of things happen. Yes.
That's also the reason why they got rid of well, I don't know what they agree. I'm sure it's on a state by state basis, but they got rid of what is it? Witness testimony, basically.
Oh yeah, witness testimony is horrible.
Yeah, well, because what might have happened was that they saw your car,
Yes.
and then it just mixed up in their brain with the car that robbed them.
Yeah. I was probably leaving at the same time as the other car did. And it was like that mine was brighter, it caught their eye. Yeah. It was like little things like that. But yeah. It was like, yep. I was totally profiled because I was from Hartford. All right. So these things can happen. So I always tell that story when I read that problem. It's the first thing was a yellow car. Yes. The nice thing, well, this is where white privilege comes into play. I was white. I can guarantee you, if I wasn't white, it would not have ended as quickly as it did. Unfortunately. But yes, they believed my wife. They did a quick search, look at the car, didn't notice any bags. and then they let me go. But yes, I guarantee that if I wasn't white, it would not have come out nearly as easily as it did. So, and unfortunately, we're still not past those times. All right, back to other issues. So let's look at this one. If any one piece on your phone breaks, could your phone die? It depends on what breaks, right? Like it wouldn't work as it's supposed to work. So a lot of times, a device or anything has multiple parts that could fail. And if one of them fails, it could break down the entire thing that needs to be fixed. So then the question comes up is that we got to look at the defective rates of all of them and determine what's the probability that things are going to break. So the first question says, what is the probability that all 4 parts are defective? So it gives you the probability of the parts being non-defective are 0.9 for A, 0.7 for B, 0.8 for C, and 0.9 for D. So what is the probability that all 4 parts would be defective? How do we figure that out? What's the probability that A is defective?
4.9.
That's the probability that it's not defective. Right. So we would do, so that is 0.1. Okay. So remember that complement comes into play, right? So if it's non-defective, it's the opposite of if it's defective. So non-defective is 0.9, defective is 0.1. So what's B? Great. C? That's the 20. And D is 10 or 0.1. Okay. You don't, so actually, if I was going to, now I'd have to figure out the defective rate for all of them, right? So I'm going to multiply them all together. And what do I get? Okay. So that's that. What I actually was about to say, because I heard people saying it, if you took that as 10, 30, 20, and 10, and multiplied those, you do not get the same answer. Okay. So when you're doing your multiplication, make sure they're all in decimal form and not percent form. All right. Same concept we were looking at it. We wanted them as fractions instead of having to do the calculations. Don't change them to the percent form. Leave them as an actual decimal. This way, your actual answer comes out to be correct. All right. If any one product breaks, the product doesn't work. If any one part breaks, the product doesn't work. So what is the probability that the product does not work? Yes. Yes. So how would we figure out the probability that it's not going to work? Yes.
Could we multiply them as when they are non-defective? Could we multiply it and then subtract it from 1? We do that.
Okay. What would that give us? Not the number. Like what concept would it give us? So if we're multiplying them all together, what does that tell us?
As non-defective, that would say the collective. That would be the collective when.
Yeah.
Not 100% sure. It would be the non-defective, like collectively, like what it would not. How often or not?
Okay, hold on. Let's give somebody else a chance to say that, and you think. Well, if we add them, we're going to get over 1, right? And that's not going to help us. Remember, probably it's got to be between 0 and 1. Even if I added the first 2, I'm over 1. So that's actually something when you're thinking about things, remember that concept. Like things have to be between the 0 and 1. So it's really easy to say, oh, let's just add it. Like, and then you're over the 1. It's like, wait, I can't have this. So it's like that's the pieces that'll help you figure out, like, okay, what something's wrong here. You're on the right path about multiplying them. So if I multiply them all together, that's going to tell me if it works, right? That would tell me if it works. So if I want the probability that it doesn't work, I would then take that piece and subtract it from the 1. That'd be the opposite of it. Because as you said, if any one piece breaks, it wouldn't work. What they wanted you to do here is go, oh, I'm just going to do 1 minus this number. And go, because that's the number when they all don't work. And if all 4 pieces had to be defective for it not to work, that'd be correct. But in this situation, if one piece breaks, the product wouldn't work. So if we multiply them, all 4 of those together, so the 0.9 times 0.7, 0.8 times 0.9, I'm going to do 1 minus 0.4536. So there is a 54, almost a 55% chance that the product is not going to work.
That's really not good.
Probably not a good idea. Okay. All right. So far, all the problems that we've looked at, the pieces have been independent. They've been separate from each other. They haven't interacted with each other. What happens if they do interact with each other? So what is the chances of me what is the probability of me drawing a king and then a queen from a standard deck of cards that are drawn without replacements? Yes.
8 on 52, but then you would the next one will multiply it, but it would be 54. Not 8. 7. Would that be it?
Okay. I got what you're thinking with the 8 and the 7. And that would be true if it said draw a king or queen first and then a king or queen. But if I want the king first, it's not going to be 8. It's going to be what? How many kings are in a deck of cards? Yeah, 4. So the king, you actually had the other concept totally correct, by the way. The king is 4 out of 52. That's my first card. My second card, I still have 4 queens, but I only have 51 cards. So that part you had right. And if it was king or queen, you would have had 7 right too. Okay. So this is where a wording thing comes into play, because if you're right, if it just says what is the probability of drawing a king or a queen and then another king or a queen, or what's the probability of drawing 2 kings or 2 queens, like that type of concept, that would be totally correct the way that you would have done it. So in this case, that's the interaction. And it says without replacement, that's the key. Because if I put the card back, they'd be independent events. They didn't have an impact on each other. But in this situation, without replacement means they had an impact on each other. So then we would multiply those two, and we get 16 over 2652, which is 0.006%. And this would work. This is the exact same answer no matter what the numbers are. It doesn't matter if it's a king or a queen. Because a 4 and a 2 have the exact same probability of coming out as a king or a queen does. So it's not less likely to get a king or a queen than a 4 and a 2. All right. I think. Let's skip that one for right now. So I want to do one more of these. All right, do this one. What do we got? What's the probability of drawing an ace of spades? Right, 1 out of 52. What's the probability of drawing another spade? Almost 51. So we have one less spade, right? Because how many spades are there normally? 13. Yeah, there's 4 aces. It's that whole English piece that comes. So yeah, there's 13 spades. So yeah, you pulled out the 1 ace. And then there's 51 total cards left because you already pulled out a card. Which comes out to be 1 out of 221 or 0.004.
Yeah.
No, so 52 times 51 is 221, 121. This is reduced.
Oh.
My calculator reduced it for me. I don't know if the iPhone one does it, but if you hit equals on the answer after the Android, it gives me that, and it also gives me the fraction underneath it. So that was kind of nice. All right. Think about like when you're playing cards, like you think, oh, these events would happen quite often. The problem is that they do, except that any one specific event has a very slim chance of coming out because there's so many possibilities in a deck of cards. Okay, because there's 52 cards in it. So like that's where like, okay, that's doesn't seem like that'd be that like that would come up quite often, but it's still less than a 1% chance.
Would be, no, that wouldn't be, that would be 52 times 52, wouldn't it? Or no, 52 out of 51. That'd be 1 out of 2,652 chance of anything happening.
Yeah.
In this theoretical sense.
Yes. Yep. If you're looking at just 2 cards, it's a 1 out of that. Yeah, 200. Yeah, that was basically what we just did. Like we did that one here, but yeah, it'd be 1 out of that. That any specific thing that you have coming out. So not a very good chance. You have a better chance of actually hitting the pick 3. Speaking of the lottery and the pick 3s, how many different numbers can you choose from on the daily 3? So does everybody know what the daily 3 is? If you ever play the lottery, there's like you have the regular lottery, like the Powerball and stuff like that.
Oh,
But you have daily games that you can play every time too. You have the pick 3 and the pick 4. Pick 3, you're literally picking 3 numbers from 0 to 9. So how many different possible combinations do you have? You have 3 numbers. Each one has to be from 0 to 9. Well, that would be a really easy game. How many numbers can you pick in the first one? 0 to 9. How many numbers? Oh. Okay, so you're missing the piece. Give me 1 second. All right, let me explain it a little better. So if you're playing the daily 3, basically you pick 3 specific numbers. Each of those numbers have to be between 0 and 9. So yes, when you play the game, you're only picking 1 number from each of those things. That is correct. The question I was asking is, how many possible numbers could you choose? Okay, so how many different ways can you come? How many different answers could there be? How many different tickets could there be? Okay, 3 numbers.
No.
As soon as I tell you the answer, you guys are going to be really mad. Yes. Yes, you could pick the same number twice. So okay, let's look at just 1 number. Okay. If I gave everybody in here the ability to pick 1 number from 0 to 9, how many different possible answers could you give me? Almost 10 because of 0. Okay, so there's 10 possible numbers for that first one. So I said, as soon as I tell you this, it's like, oh. Okay, so that's number 1. The second number also would have 10 possible combinations, right? And the third one would also have 10 possible combinations. So the fundamental accounting principle states that if we multiply all those, we'd get the total number of possible combinations we have. So in this case, we'd have 1,000 combinations, which completely and utterly makes sense because the numbers would go from 000 to 999, which is 1,000 numbers. Okay. I know. More complicated than it sounded. I know.
All the possible combinations.
Well, that's the thing. And actually, that's what we just did. We counted. The only possible numbers that you could pick for this would be from 000 to 999. No. It's 1,000. Multiply. You got to calculate.
110 times.
All right. The nice thing is the multiplying tens, you just count the zeros. So if I had 4 tens, it'd be 10,000. All right. Let's think about phone numbers. Okay. So we're going to ignore the area code for right now because the area code is very specific. And actually, the next 3 digits are very specific too, but There's so many of them, it doesn't actually matter. So how many digits are in a phone number? So we're ignoring the area code. So there's 7 numbers because it's area code, right? And then 3 numbers and then 4 numbers, right? So there's 7 numbers, right? And each of those digits can be what? Between 0 and 9, because those are the only numbers on your phone. So I have 10 times 10 times 10, and then 10 times 10 times 10 times 10. So how many different phone numbers could I have?
Billion.
1, 2, 3, 4, 5, 6, 7 zeros. I could have 10 million phone numbers. Before cell phones kind of changed the game a little bit. Your area code was based on the state. So right now, Connecticut used to only have 1 area code. It used to be 203 for the entire state. And then they added 860. And now they added 417. And there's another one, and I can't remember what the other one is. I think it's 9 something. So there's 4 area codes in the state of Connecticut now. It might be. I can't honestly remember what the other one is. The only reason I know 417 is because that was my parents' area code for their business in Meriden. So 959. Okay. So the area code is for basically the state, and it's supposed to be split up by areas, but that's kind of merged a little bit now too. The next 3 digits in your phone number is the prefix that actually was telling the operator where to send your phone call. So like it was more like towns or neighborhoods had their own prefix. And the only ones that were random were the last 4 digits. So as long as that area didn't have more than 10,000 phones, you were fine. Yes.
Correct me if I'm wrong, I always assumed that they weren't random, that they're like, it's numbering you. So it's essentially, it's just your assigned number that you were given.
The last 4 were randomized.
Oh.
They weren't the last 4 were randomized. The 3 in the middle were not. And the area code was not. So that basically was the state you were going to for all intents and purposes, the town, and then there was a random number assigned after that point. Because if it wasn't random, you could easily literally just like go look at get your neighbor's phone number because it would have been pretty much in order. So the Social Security card number is actually the same concept. The first 3 and the middle 2 have actual meaning. The last 4 are randomized. That's why they always ask for the last 4 of your Social Security number, because the rest of them actually mean something. Those are just 4 random numbers. All right, let's look at a license plate. So, and actually Connecticut was the same way up until they went to 7 digits. So in Connecticut and Utah, you had 3 letters and 3 numbers in your license plate. So how many different license plates could there be? So if you had 3 numbers, okay, now let's go back to those numbers again. How many possible numbers could I have? Right, 0 to 9, 0 to 9, and 0 to 9, right? So I had 10, 10, and 10. Now, letters. How many letters? Missing the 3, yeah. So how many letters in the alphabet? Minus the 3. 23. Why did they take those 3 away? Yeah, that one looks like a 1, that one looks like a 0, and the Q looks like a 0 too, because it's really hard to make out that one little squiggly on the end. Okay, so how many license plates are there? I think you're off by 1-0. Oh yeah. Just over 12 million. The states ran out in license plates because they actually eliminated quite a few other ones in there. But that's why Connecticut actually went to 2 letters and 5 numbers now, because there wasn't enough combinations of the other license plate to keep giving new ones for cars and whatnot. So now if we look at Connecticut's is now 2 letters and 5 numbers. So if we eliminate the same 3, we'd have 23 times 23 times. So do we got more numbers, more license plates, or less? Now we're up to 52 million license plates. We only have like 3.5 million people that live in the state of Connecticut.
Only has like 14 million people.
So, well, yes, and then there's also the customized plates. Like I said, there's things that they won't put in play, and or sets of numbers that they won't use and whatnot. You can, yeah. So, but it's normally pretty obvious that it's a customized plate. So they look at those a little differently. Yes.
Does New York City have 20 people? There's 8 million people in New York. Is it New York City?
Yeah.
All right, then never mind. That wouldn't work. I would just think at like some point wouldn't, like Tokyo has its own municipality, doesn't it?
Yeah, Tokyo's I think around 14 million people now.
So wouldn't it be so at some point wouldn't theoretically a city have to start making its own license plates? In a theoretical sense, because
No, they would just increase the number of whatever digits or whatever else they're using. So, all right, I'm running out of time and I got to get through these last 2. Most of the time, we're not just looking at a single set of values like we were there with the numbers. We're looking at orders of arrangement. So we're going to be putting things in specific orders. So when you play the lottery, does it matter which order the balls come up? When you play the regular lottery? No. The order doesn't actually matter. It's just a random set of balls, and as long as the numbers come up, and actually on your tickets, they're always in numerical order. You don't get to choose the order, so that doesn't matter. However, when you're playing the daily 3 or like those numbers we're looking at, order does matter. 345 is different than 534, for example. The order does actually make a difference in that respect. So there's 2 different sets of things that we can look at. There's a permutation and there's a combination. You will see these 2 symbols on your calculator. And if you actually, I'm not sure if the regular calculator has them or not. Let's look real quick. I don't even know if you turn it to scientific if it actually has them. It does not. Yeah. So this would be using the Desmos calculator would actually be the easiest way to do this. So I will show you. So on the Desmos calculator, if you go to function, you'll see these 2 buttons right here. NPR and NCR. That's permutation, that's combination. Okay. What those have us do, so permutation is when there's a specific order. So permutation, order matters. Okay. I'm not going to have you do this wonderful calculator formula right here. We're going to use the calculator to do that. Okay. So for permutation, you're just going to use that NPR button. So permutation is where order matters. Like this situation. we have 7 people running in a race. How many ways can they finish first, second, and third? So does order matter? Yes, because first and third is not the same thing. Okay. So when we're looking, so this is a permutation. So we're going to use NPR. N is the number that I have. So that's 7. R is the number that I want. How many positions am I looking for? 3. So that's 3. So depending on how your calculator does it, you're either going to do 3 NPR 7, or sorry, wrong way. 7 NPR 3, or NPR 7, 3, depending on how your calculator is set up. Desmos is the second one. And we get the answer of 210. So there's 210 different ways that that race can finish. Yes.
So like, how did you bring up the NPR on the calculator?
So on Desmos, you hit the, see where it normally starts off here, click function. And it's going to be right there.
Does it matter, like, if say my mixed up, like, with the 3 where the 7 is, that affects?
It won't act, I don't think it'll actually give you the answer. I think it'll say undefined. Yeah. Or it'll say 0. The bigger number always has to go first. Because it's basically, it's called 7 choosing 3. And I can't do 3 choosing 7 because I didn't have 7 to choose from. So that's how you do the order. So the bigger number will always be first in the, and both cases that we're going to look at. Okay. Does that make sense? Okay. Now, if I did 10 choose 3, I don't get 1,000, right? The reason being is once it's chosen, it can't choose it again. So when you're looking at permutations and combinations, you're not going to choose the same thing multiple times. It's only choosing it once. So once you pulled that sprinter out in that situation that we did, they can't finish first, second, and third. Okay. So that's why we have that fundamental accounting principle that we have to do that part there. Because in this case, you're only choosing each one possibly once. So we have a situation that we come up with like this. What happens if the options repeat themselves? So like in this situation, I have 4 S's. So this one we do have to actually use this crazy formula, but we're going to use it on Desmos anyway. I'm going to show you how to do that. So the top number is the total numbers that you have. So how many letters are in Mississippi? It's probably the only state that everybody can spell without even thinking about it. 5, 6, 7, 8, 9. Yes, 11. All right. Now, the bottom ones are going to be each of the letters. So how many M's do we have? How many I's? Four. Right? Yes. 4 I's. There's 2 S's. Oh, 4 was 4 P's and 2 S's, right? Okay. So when you type it into Desmos, next to those NPR and NCRs, there's the little exclamation button. The exclamation button is a factorial. It basically means we're going to multiply all the numbers all the way down. So 4 factorial means 4 times 3 times 2 times 1. That's what that factorial button means. So it's an actual mathematical operation, not just an exclamation point. So on the top, I had 11 numbers, 11 values. And on the bottom, I have each of the letters with how many of those I have. So I have 1 M, 4 I's, 4 S's, or 4 P's, and 2 S's. Or vice versa. 4 S's and 2 P's.
Why do we need the exclamation?
Because it actually is an operation. So that so example, 4 I or 4 factorial is 24, not 4. Because that means 4 times 3 times 2 times 1. So the factorial actually means something. That's an actual operation, just like addition, subtraction, multiplication, division, things like that. So that's why you have to put it, otherwise the calculation won't come out right. Because like 11 factorial is a really big number. Because it's the same thing as saying 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what the 11 factorial is. So instead of having you write out all this, you write the exclamation point. A lot simpler. Okay. All right. Last one. Combinations. Combinations are when order does not matter. Oh, I didn't switch back over. Combinations are when order does not matter. Okay. So the big difference is permutation order matters. Combination order does not matter. Okay. So if I was picking people for a committee, okay, I'm going to pick three of you in here for a committee. Does order matter on where I pick you? You're all going to be on the committee, right? So in that situation, order wouldn't matter. So I would use combinations. If I was going to pick you for president, vice president, and secretary, does order matter? That would be a permutation. Okay. That's the big, going back to that English thing. That's the biggest difference between the two. They're not basically done the same way. They're going to be using an NCR and NPR. It's order matters and order doesn't matter. So I'm going to select 6 songs from a CD containing 12 songs. Does order matter? No. Doesn't matter the order I put the songs in. I'm picking 6 out of the 12, right? So since order does not matter in this situation, I'm going to use the C. N is still 12. R is still 6. That doesn't change in how you're typing them in. So I would have 924 different possible playlists. And I'm just picking 6 songs from 12, or 6 songs out of 12.
12, 6, or 6, 12.
Yes, you can't do the other direction. The big number always has to be first. If order mattered, I'd have 665,000 different playlists. Okay. So if order mattered, you're going to have a lot more. Since order doesn't matter, we would have a lot less because it doesn't make a difference if the song is first or last. All right. Last one. How many 5-card hands can be dealt from a deck of 52 cards? How many 5-card hands can be dealt from a deck of 52 cards? So, question, does order matter or not matter? Does not matter, because I can move the cards any way direction I want, right? Okay. So the order does not matter. So we're going to use combination or permutation? Combination. N is what? And how many? And R is 5. So 2,598,960 different hands can come out of a deck of playing cards. Yes.
Where's the R come from? I had the equation as K.
Oh, K and R is the same thing.
Oh.
I don't know. There's certain things this book does that does not make sense to me. Like every calculator in the world is NCR and NPR. They use a K.
So what does the R actually mean?
It's it's R is basically the number that you're choosing. So, and they couldn't use a C because they already had a C, so they used R. But yeah, every calculator is NCR and NPR. I don't know why the book uses K. Yeah. So things I will not do in my stats book. All right. You should be able to actually do all the stuff for chapter 6 now. Monday is Columbus Day. We do have class. The school is open. So